All right, hello chemistry students. Today we're going to be looking at pH calculations with respect to strong acids and bases. So the first thing we want to know is what is the pH scale? And the pH scale is a logarithmic based scale, and it's a measure of acidity. So it's a way for us to describe how acidic various acids are. It's log based. So what that means is that every digit we change is a factor of 10. So if something has a pH of 3 and something else has a pH of 2, the 2 is 10 times more acidic. It's a number line, right? So typically we think of this as scale. 7 is neutral, straight in the middle, right? That's kind of the basic. Anything that's less than 7 we consider acidic. Anything that's greater than 7 is basic. Now, typically for the purposes of our class, we'll look at things that range from 1 up to 14 is kind of the normal range that we'll see things. But obviously the scale extends in either direction quite a bit. Now, the pOH scale is the same exact thing, and this can become helpful in terms of doing some of the calculations a little bit later on, but it's just a measure of how basic something is. So it's a measure of how basic a solution is. It's the exact same scale, except it's flipped. It's also log-based, so it's base 10. It ranges typically for us from 1 all the way up to 14, with 7 right in the middle being neutral, except in this case, bases are going to be our smaller numbers and acids are going to be numbers that are greater than 7. So it's the same thing. It's just the exact opposite of the pH scale, and that can be useful sometimes if we're doing some calculations. So using pH, one of the equations that we'll often use is determined by the self-ionization of water. This is water reacting with itself. And if I think about this in terms of equilibrium, we've talked about this before, I see two states of matter that are liquid. Remember, we ignore liquids in an equilibrium expression. So if I write a KEQ equation for this, I'm looking at the amount of acid, the H3O plus, and we can use H3O plus equivalent to H plus. You'll see it written either way depending on what book or what resource you're using. So those two terms are synonymous. They're the same. So H3O plus times my concentration of OH minus. Now, because both of these only have a coefficient of 1, they're just to the first power. And if you measure this, if you look at water, we call this the KW. It's always going to be the same number. And it ends up being, this is our first equation down there in the bottom left here, the KW of water is always 1 times 10 to the negative 14th. This is the K value for water at 25 degrees Celsius. So what that tells us is that if I have just a glass of water, then I know that the concentration of the acid in the water is going to be 1 times 10 to the negative 7th, and I know that the concentration of base in the water is also going to be 1 times 10 to the negative 7th. Now this becomes useful because if I take those numbers and I plug that into our equation 2 on the list here, I can get the pH of pure water. So if I take the pH, which is the negative log of the H plus concentration, and I take the negative log of 1 times 10 to the negative 7th, I get a pH of 7, which is where we get a pH of 7 being neutral. So this becomes useful in terms of basing our scale of acids and bases, with water falling directly in the middle between the two as a neutral substance, both an acid and a base, but equal amounts of each. Now the other equations here are also useful. We have equation 2, which is pH equals negative log of H plus, the one we just used. If you wanted pOH, you would just have to take the negative log of the OH minus concentration. Now, if you've dealt with logs in math class, you'll know how to rearrange logs. If you don't, we have the equations listed out here. So if I wanted to solve backwards for equation 2, and I wanted to solve for the H plus, I would do, because we know logs are base 10, I would raise 10 to the negative pH power. And if you're not sure how to rearrange logs, you haven't learned that in math yet, don't worry about it. You can always consult these equations. It makes it easier for you. If you want to know how to rearrange the pOH equation, well, then that's equation 5, right? The OH minus concentration is going to be equal to 10 raised to the negative pOH power. So when we start solving for these mathematically, there is a new rule for sig figs when we start talking about logs. So if I wanted to just do a couple of practice problems to show you the sig fig rule, it says if the H plus concentration in a solution is 2.421 times 10 to the negative 5th molar, then what is the pH of that solution? Now, if I look at this initial given number, this number has 4 significant figures. I'm looking at the digits in the front there, right? 2.421. I don't worry about the times 10 to the negative fifth. I just look at those digits in front. If I wanted to solve pH, I'm going to be using equation 2. pH equals negative log of the H plus concentration. So for this problem, I would take pH equals the negative log of 2.421 times 10 to the negative fifth. And when I plug that into my calculator, I'm going to take negative log 2.421 second E negative 5. I get 4.616005211. Okay. When we deal with logs, the number in front of the decimal place does not count towards your significant digits. So if I wanted to round this number, I want to keep it to 4 sig figs. What that means is in my final pH answer, I'm looking for 4 digits after the ones place. So I would look at the next 4 digits, 6160. The next number after the last 0 is another 0, so I don't round, but I would leave all 4 digits. What that tells me is 4 decimals equals 4 significant figures. So to keep my sig figs the same as my initial given number, I'm keeping 4 decimal places. So this is kind of the rule that you can think about. The number of sig figs in your molarity, which is our given concentration, right, whatever we started with, is going to be equal to the number of decimal places, the number of decimals in the pH value. So it's a weird rule. We're looking at the number in front as not counting. The ones place doesn't count. It's only the decimals that we're worried about. Now, if you're undoing it, if I wanted to use equation 4 to undo a log, if I look at equation 4, I have H plus is equal to 10 to the negative pH power. I would do the same rule, but in reverse. So if the pH of a solution is 3.69, then what is the H plus concentration? Okay, so I'm going to plug in H plus equals 10 to the negative 3.69 power. Now, if I want to know how many significant figures that digit has, I'm only looking at the number of decimals. Because it has 2 decimals, that tells me that this number has 2 significant figures. It's a log-based number, so I'm only looking at the decimals. So when I plug this number into my calculator, I'm going to get H plus is equal to something, and I'm only going to record the first 2 digits. So I'm going to type 10 carats negative 3.69. And I get 2.04 times 10 to the negative 4th. Now, I'm only going to write down the first 2 digits. I only want 2 sig figs. Because it's 2.0, the next digit's a 4. I'm not rounding. So my final answer is 2.0 times 10 to the negative 4th molar. Because, again, I only had 2 decimals, I only want to leave 2 digits in my molarity. All right, let's do a couple of practice on the next page. So if I want to know what strong acids are, well, these are going to be any acid. We looked at this before. This is going to be anything, if you see strong, this tells us that it's going to dissociate 100%. Now, we're going to talk about weak acids in a little bit, but strong acids, they always react 100%. There is no equilibrium here. It's 100% forward. And the strong acids are the ones that we've commonly used throughout the year. Hydrochloric acid, nitric acid. We have hydroiodic acid, sulfuric acid. We have hydrobromic acid, sulfuric acid, H2SO4, and then perchloric acid, ClO4. So any of these 6 acids are going to react 100%. Now, strong bases, you're usually looking for just the hydroxide ion. That's the key thing. Anytime you have an alkali metal, anything in the first column of the periodic table, plus an OH, you know that's going to be strong. So anything like lithium hydroxide, that's strong. Sodium hydroxide, that's strong. Anything in the alkali metals. There are a couple of alkaline earth metals that are also, it's usually CBS is the way to remember this. That's calcium, that's the first one, barium, and then strontium. So those 3 alkaline earth metals plus hydroxide are also going to be strong. Now, because these ones have a +2 charge, you would have something like calcium hydroxide, where you have multiple hydroxide ions. So that's something to pay attention to when you're doing the math. You would have 2 hydroxides for every one of the initial ionic compound you start with. So something to pay attention to. All right, what would a couple of practice problems look like? Well, let's put it all together. If I'm looking at this first problem, so it says, if I have a solution of 0.01 molar hydrochloric acid. Hydrochloric acid, that should jump out to me. I think, okay, this is strong. This is shown as a double-ended arrow in my equation. In my head, I'm going to think of this as only a forward arrow. It's 100% forward. And if I set up an ice table here, I can kind of think about this as my initial concentration, 0.010, and I have no hydrogen and I have no chloride ions. And then if it reacts, I want to think about how much my change is going to be. Well, if I know that it's strong, I know that 100% of it's going to react. Every bit is going to react, which means that all 0.01 molar is going to react. So typically, we don't even need to do an ice table for a strong acid. You just know that there's going to be none of the original acid left over, and that your concentration of the hydride ion, which is the one that we're going to care about in terms of our calculations, is going to be equal to whatever your starting concentration of the acid was. So this becomes our important part. The chloride ion, not really too worried about. So if I want to solve for pH, I'm taking the negative log of my H plus concentration. pH equals negative log 0.010. Plug this into my calculator. I'm going to take the negative log 0.010, and I get 2. Now remember, the sig fig rule for logs, 2 in front of the decimal does not count towards my sig figs. So if I look at that number had 2 significant figures. So that means I need 2 decimals in my answer. Well, currently I have no decimals. So that means I have to add some extra zeros. So my final answer would be pH equals 2.00. I would have those 2 decimals to show. All right, let's try another one. What if I have sodium hydroxide? Okay. Strong again, right? I see it's an alkali metal plus sodium hydroxide. So I don't even need to do the math. If it's strong, whatever my concentration of sodium hydroxide is going to be equal to my hydroxide concentration. 100% of it reacts. So that tells me that my hydroxide concentration for this problem is 0.010 molar. So that's my idea. I don't need the M there at the brackets. Tell us molarity. So then if I want to solve, there's 2 options. The first way that I could solve this, because I'm trying to get to pH, but this is a base. So I can't just plug in the hydroxide concentration to my base. So my option 1 is to use the hydroxide concentration to solve for H plus concentration. And I could use my first equation from the previous page in order to do this. Once I get the H plus concentration, then I can take the negative log of that H plus in order to get my pH. The second option, using my 6 equations, which will also get you to the correct answer, is I would use my OH concentration to solve for pOH, which again is not the typical unit that we use when talking about acids and bases, but it becomes useful in terms of doing the math. And if I know the pOH, then I can subtract pH plus pOH equals 14. These 2 numbers added together always add up to be 14, and I can figure out the answer there. So, all right, let's jump ahead here. I already just copied and pasted in the work just so we can talk about this since we're running out of time here for keep this video under 15 minutes. So if I use the first strategy, I can see I would use the Kw equation, 1 times 10 to the negative 14th equals my H plus times the concentration of OH minus there. And then that gives me an H plus concentration of 1 times 10 to the negative 11th. Taking the negative log of that number, I get the number 11, but because I want 2 significant figures, I have to add those 2 decimals. So I get 2 sig figs in my final answer, and I get the number 11.00. I would get the same exact answer if I used the second strategy. By taking the negative log of that original number, I get the number 3, and then to add to the 2 significant figures, I add 2 decimals, and then subtracting that number from 14, I would get the same final answer. So you have some choice when using these 6 equations to solve pH problems. The nice part is strong acids always react 100%. So whatever your given concentration is going to be the concentration of your hydrogen or your hydroxide. Hope that helps, guys.